Hello, my name is Santiago Balseiro. I'm going to talk about learning in repeated auction with budget, regret minimization, and equilibrium. This is joint work with Yonatan from Stanford University. So the motivation from this talk comes from repeated auctions that are sold to, used to sell online ads. So advertisers in this market typically specify budgets to limit their expenditure. And budgets are very common and a very natural way they have to limit the amount of money that they want to spend in a given horizon. Now, what's interesting with budget is that they're going to couple decisions across the horizon. For example, in the case of a second price auction, if you know your value, bidding truthfully is no longer optimal. What you want to do is you want to shade bids to take into account for the option value of future opportunities. So as a result, what happens is that budget needs to be paced across the horizon. And also in this market, there is a lot of uncertainty in the sense that advertisers may be uncertain about the competitor bids and also about the future value they have for the opportunities. And these uncertainties makes pacing budget challenging. So in this talk, what we're going to discuss is how should budget-constrained advertisers bid in the presence of uncertainty and also in the presence of competition. And before moving forward, let me point out that budget pacing has attracted a lot of attention in the industry. These are like screenshots showing documentation from Twitter, Facebook, and Google describing how advertisers should pace budgets. So going back to the problem, if you think about the problem, what advertisers are doing is that they're solving a dynamic optimization problem with some global constraints. So we can think about different online models to tackle this problem. One is a stochastic model, and this is predicated on the fact that most advertisers have very good forecasts for, like, for example, future opportunities or competing bids. And in this model, you would assume that values and competing bids are drawn I/D from a distribution that is unknown. Then, as a benchmark, we would try to compare against the best performance in hindsight. I'm going to describe this benchmark in detail later, but basically what it means is that at the end of the horizon, you look back and say, like, OK, which action should have I won? What you can obtain here, you can obtain long-run average optimality. Essentially, you can obtain vanishing regret. The pros of this model is that you're going to get very nice guarantees, but the cons is that you're going to have like strong statistical assumptions because in reality, the world is not going to be IID. So the other approach is assuming like kind of that bids and competing values are adversarial. Essentially, you are making no statistical assumption. This can come in arbitrary ways, and even you can have an opponent picking them in a way to hurt you the most. So in that case, you can look at the same benchmark. Now, in case of attainable performance, you won't be able to obtain vanishing regret. What you can obtain is a constant factor approximation. So that's kind of disadvantage that the guarantees are going to be more conservative, but this is like kind of more robust. So we're going to do in this talk also, we're going to look at the third model, but it's going to be the case of simultaneous learning. We're going to think, what if we have advertisers learning at the same time? So for example, if values were IID, now competing bids will no longer be IID, and these are going to be non-stationary endogenous, with the dynamics going to be dictated by the learning strategy that different advertisers are adopting. So in this case, we can think about as a benchmark the least feasible dynamic deviation, and you can take into account that now your actions may impact the strategy of your competitors. So now the environment is going to be endogenous, and we can hope for is an epsilon Nash equilibrium. So again, the advantage of this is that, again, you can make good guarantees, but we're going to have some strong behavioral assumption because you're assuming something about what your competitors are doing. So what we try to do in this talk is we try to design strategies that attain good performance in all models, that perform well in the stochastic, adversarial, and also when they are simultaneously adopted by all players, they lead to an epsilon Nash equilibrium in large market. And there is a lot of literature on learning in games on repeated games, so we're not going to go over all this literature. I'm going to just point out what are the difference with this stream. So in this stream, what people assume that you're competing against the best static action in hindsight. In this paper, what we're going to do is we're going to compare with the best dynamic action. Because of the budget constraint, doing a single action in static may not be feasible because you may violate your constraint. So there is a lot of literature in learning in sequential auction, and Balseiro has done a lot of work on this. Now, the difference with that literature is that most of the literature focuses on learning the value. So here, we're going to assume that once you see the item, you know the intrinsic value for the item. So you don't need to learn the value. What you need to learn is how to bid based on this value. And why you don't want to beat this value? Well, because of the budget constraint, you may shade bits. And we try to understand how you should essentially shade the bits. So there's a lot of results on dynamic optimization with budgets. For example, the papers on budget with bandwidth and Suo et al. That they look at different adversarial and stochastic models. So essentially, here we try to bridge these two models and also look at the case of simultaneous learning. Also, we have some work on reproduction with batches. So here they assume that the distributions are known. And also, we want to make a connection with this literature of simultaneous approximation for an algorithm, or the best of both worlds literature that try to find strategies that perform well in an adversarial and in a stochastic setting. And we complement that by looking at the case of like simultaneous learning. OK, so we're going to start with a simulation of a model. Then we're going to describe the algorithm and then performance against arbitrary bits. And then I'm going to talk about the case of simultaneous adoption and what happens if you get an epsilon equilibrium or not. So the model, we're going to have a time period on a horizon of length t. In each time period, we're going to have an item that's going to come available for sale. We're going to have k advertisers. Each advertiser is going to have a budget constraint. It's going to have a budget bk. So when an item arrives, the advertiser is going to observe the item and is going to learn the value. So once you see the item, you know what's the value. And this value is going to be drawn from some distribution that advertisers don't know. And they're going to post a bid. And then what we're going to do is the auctioneer is going to run a second price auction. And this is going to determine the allocations and the payment. Now, we are interested in this special regime where you have like many small interactions. Essentially, budgets and the length of horizon are going to be long. And we're going to assume that this scale at the same rate. And we're going to fix the target expenditure rate rho. This is going to be an important quantity that is going to be essentially the ratio of budget to time. For example, suppose that you have $1,000 and you participate in 100,000 auctions, and this rho is 1 cent. So essentially, you would expect, on average, to spend 1 cent per auction. And values are going to be bounded with some support. And again, this regime is well motivated in this market where typically advertisers participate on millions of auctions per day. So in terms of our model, again, the advertiser K is going to be characterized by type. That is going to be the row, the target, and the distribution of values. Only it's going to know the row. It doesn't know the distribution of values. What do you observe? Well, at time B, you're going to observe the value. And based on this value, you're going to post a bid. Then we're going to denote by DKT the maximum competing bid. That's going to be the maximum of the bids that I'm facing in the auction. And also what we're going to observe is the payment. So what's going to be the payment? Now, in case you win, when the competing bid is less than your bid, then you're going to pay the competing bid. This is the second price auction rule. And in case you don't win, then your payment is 0, and you observe that 0. So what's going to be adaptive strategy? Adaptive strategy is going to be a mapping from history to bid. That's going to determine how you should bid. With the objective, what you care about is the total net payoff. So given a sequence of bids and competing bids, the total net payoff is going to be simply the sum of the values minus the payments over the auctions that you won. And this strategy should be budget feasible in an almost sure sense. It should be the case that in every sample path, the amount of money you spend, so this is the win you auction and you pay, should be less than your budget. Now here I want to stress that advertisers are uncertain about competitors. They don't know how many competitors they are. They don't know the distribution of values, their bids, or what kind of strategies they are using. So let me start describing our benchmark in the case of arbitrary bids. So here we're going to use the concept of gamma competitiveness that is well defined in the online algorithm literature. So given a sequence of values and competing bids, we're going to let this pi h to be the best performance in hindsight. So what we're doing is that after the end of the horizon, then you look back and you look, OK, which actions I should want given my budget constraint. So what's the best possible set of actions that I should have won? And this, if you think about it, is just an abstract problem. Now we're going to call a strategy gamma competitive, asymptotic gamma competitive, if the performance of the hindsight strategy is at most gamma of the performance of my policy. And here we're taking the supremum over all potential sample paths, all realization of values. And these here I'm assuming that these are bounded and competing bids. And this, if you want, you can also allow them to be adversarial, then you have like an adaptive adversary picking them that we can allow to. And also we're doing this in the limit. So we're doing the asymptotic while scaling t and the budget proportionally according to rho. And this is important. We do the asymptotic because we don't care about the rate of conversions. We just want to look at the first order terms. And this guarantees a fraction 1 over gamma of the best performance in hindsight. So for example, if it's too competitive, you're going to get like 50%. And what we want this gamma is to be small. And also I want to point here that compared to the learning literature, this is also a point of departure in the sense that we're not competing against the best static action in hindsight. Here, this benchmark is potentially dynamic, and it can choose which options to win. So what can we hope for? Well, we have a result that says like no strategy can achieve a competitive ratio lower than gamma star, where gamma star is essentially the ratio of the maximum value to the target expenditure rate. And I'm going to go over this quantity. I'm going to describe the intuition for this next. But the first question that comes to mind is, one can achieve gamma competitiveness? And the answer is yes. Let me give you a very simple strategy that achieves gamma competitiveness. This is what we call the adaptive pacing strategy. And this for an advertiser K. It's going to have a strategy that's going to have one input. It's going to be the step size. And this step size is going to be a parameter that can depend on the time horizon. It should go to 0 as the time horizon becomes longer, but not too fast so that you have enough mileage to learn. And the strategy is very simple. What it's going to try to do is going to try to shade bits according to a multiplier. And what it's going to do is going to update this multiplier using like kind of a simple update rules. And similar strategies are used actually by practitioners in the real world. So what is going to happen is that you're going to start with initial multiplier. In every time period or until you run out of budget, you're going to observe the value. And you're going to post a bid. That the bid is going to be essentially your value divided over 1 plus mu, where plus 1 mu k is essentially your multiplier. Then you observe your expenditure, and you update your multiplier according to this simple update rule. So let me describe the intuition. So here what you're doing is, again, balancing present and future opportunities. And the intuition is that if you're spending more than the target, if you're spending a lot, what's going to happen is that the multiplier is going to go up. Now, if your multipliers go up, then you're going to shade bits more, and then you're going to spend less in the future. So essentially, if you're spending money too fast, what you're going to do is you're going to lower the bits. And mathematically, what we're doing is that you can think about this mu. Essentially, we were trying to approximate. This is just the Lagrange multiplier of the budget constraint. So what we're doing is essentially a gradient descent method in the dual space. So this is essentially a gradient of the dual objective function. Okay? So about performance, recall that no strategy can achieve a competitive ratio better than gamma star equal to V bar over rho k. So while this strategy happens to be asymptotic gamma competitiveness, and then essentially achieves a fraction 1 over gamma star. Let me describe a little bit more this ratio, what it means. This is essentially rho k over V bar, that is the target expenditure, what you should be spending per auction, divided V bar, that the maximum value is essentially the maximum possible expenditure that you can have. So essentially, this ratio, what captures is in relative terms how budget constrained you are. Now, if you have plenty of budget, then the problem is going to be very simple because being truthful is going to perform well, and this can be well approximated. Now, if you are very budget constrained, then the problem is going to be hard to approximate, and these strategies are going to perform worse. So again, this strategy is very simple, and also it's robust. So here we make no assumptions. Bits can be correlated in any arbitrary way, or even adversarial. And also, we can show that in the case where bits and competitor bits, values and competitor bits are IID, actually this is long-run average optimal. Essentially, it has vanishing regret. So this corresponds to the case of gamma equal to 1. And the proof idea, what we do is we extend singulation learning ideas to this primal dual scheme. And because we're learning in the dual space, we need to worry about like guaranteeing primal feasibility and also primal performance. Now, the most interesting question for us is what will happen if all advertisers are implementing or adopting similar strategies at the same time. So the first thing that we can show is that we can show that the multipliers that they're using and the payoff they obtain, they're going to converge to a steady state. And this steady state is going to correspond to the fluid mean-field equilibrium that we developed in previous papers. So like even when all people adopt these strategies, the dynamic system that is in use is going to be stable and it's going to converge to a steady state. And also another question is trying to find out whether this is an equilibrium or not. And we're thinking of equilibrium, we're thinking about deviations to kind of dynamic strategies that can try to kind of deplete competitors or so on. So what kind of deviation do? There are two sources of potential gain from deviating. For example, if I know all of advertisers are using these strategies, how can I cheat the system? Well, I can try to make my competitors deplete their budget early so that I can remove them from the market. For example, this is an example. This is the length of the horizon. Suppose that one competitor, this green path shows his budget, and he has some budget remaining. So what I can try to do is I can try to force him to deplete early, and then if I remove him from the market, then I'm going to have less competition and I can do better. Other thing that I can try to do is I can try to force my competitor to learn a wrong multiplier, potentially a higher multiplier that's going to reduce their bids and essentially reduce competition. Now, what's interesting is that when all advertisers follow adaptive pacing, one is never effective. Now, because of the self-correcting nature of these adaptive pacing policies, then you can never force your competitors to run off budget too early. But if you have only a few competitors, two may be effective. What you can do is you can try to game the system and force them to learn something that is wrong that may benefit. So what we can show is that under various conditions that are relevant to practice, we can show that this actually is an approximate equilibrium in a large market when you have enough players. And let me give you such an example of a setting where this would hold. Well, this is an example where you have like parallel auctions. Imagine that where you have like, instead of having one media site, you have like M of this. And then at each point in time, each advertiser is going to participate on one of these media sites at random. And we're going to look at the case, again, when you have many interactions and when you have like a large market, in the sense that you have like many of these media sites, and then advertisers are going to participate in one of them, and there are few competitors per auction. So basically what we want to achieve is that in each time period, you are not competing with all advertisers, you are only competing with a subset of advertisers, and in that case, the impact that a single player can have on the system is essentially limited. So what can we show there? Well, actually, we can show that this constitutes an approximate Nash equilibrium in dynamic strategies. So imagine that you come to this market, and you know that all competitors are using these kind of strategies, and you want to try to find what's the benefit that you can get from unilaterally deviating to any other feasible strategy that is potentially dynamic. So we can show that this benefit of deviation converges to zero as the market grows larger. So essentially, we show that the payoff that you're going to get from deviating compared to the average payoff you get from playing the strategy that we propose, this is going to be at most epsilon, and this epsilon is going to grow to zero as the number of time periods and the number of players is going to increase. And also, I'm going to point out that here, this equilibrium concept includes deviation with complete information. So here, we're allowing deviations that know how many players are there, know the distribution of values, know their budgets, and even know what kind of strategies they're doing. And also here, again, we show that this epsilon is small in many realistic markets. So takeaways, what we do, again, we study like competition between budget-constrained advertisers in an environment when there's uncertainty about the distribution of values and potentially the strategies of sophistication of the competitors. And we propose a very simple, the adaptive pacing strategy that essentially extends idea from simulation learning to a case to kind of essentially to adaptive balance the value of future opportunities. Also, we have data from actual exchange, and we show that in this practical setting, these strategies perform very well, so they perform way better than our worst-case guarantee. And essentially, we're going to finish with this table where we compare the performance of the same policy across many settings. We showed like in the stochastic setting, it's long-run average optimal. Essentially, it has like vanishing regret. If in the adversarial setting, it's going to be V bar over gamma k rho k competitive, and we show that this bound is tight in the sense that no other strategy can perform better asymptotically. And also, we show that if all advertisers implement this strategy at the same time, we're going to show that it converges to a nice steady state, and also it constitutes an approximate Nash equilibrium in large markets. Thank you.